My name is Peter Connor. The title of my talk is The Construction of Doubly Periodic Minimal Surfaces via Balance Equations. I want to thank the organizers of the Geometric Analysis Past, Present, and Future seminar for the opportunity to speak. This work is a joint work with Matthias Weber from Indiana University. So, our outline of the talk, we'll go over some background information for doubly periodic minimal surfaces, discuss our results, the Trizet regeneration technique, and do a sketch of the proof, and also look at some other possible limits for the doubly periodic minimal surfaces. A surface in R3 is a minimal surface if it has constant mean curvature, h equal to 0. Surface has mean curvature 0 if and only if it is locally area minimizing. And minimal surfaces parameterized as a graph over a domain in the plane satisfy a nonlinear partial differential equation, although I won't be using that for my methods. One of the first known examples of minimal surface is the catenoid, discovered by Euler in 1741. It's parameterized, the top half parameterized as a graph over the plane with the third coordinate given by the Cauchy inverse of the square root of u squared plus v squared. It's the first known example of a non-trivial minimal surface. It is the only embedded minimal surface with genus 0 and more than one end. The helicoid, discovered by Meissner in 1776, is parameterized as a graph over the plane with the height function given by the tangent inverse of the u over v. It's the only non-trivial, simply connected embedded minimal surface. The helicoid has genus 0 and one end. Shirk's doubly periodic surface was discovered in 1835, parameterized as a graph over the plane with the height function given by the log of cosine of u divided by cosine of v. It's the first known example of a doubly periodic minimal surface, has genus 0 and four ends in the quotient. So we'll utilize what's known as the Weierstrass representation for a minimal surface. If we have a minimal surface parameterized using a conformal parameterization, then the coordinate functions are harmonic functions, and each of them can be expressed as the real part of a meromorphic function. So if we let G be the composition stereographic projection composed with the normal map, and let DH be the holomorphic extension of the third coordinate differential, then if we say let X be the map from the domain sigma to our minimal surface M in R3, we'd say if it's minimal, then the Weierstrass representation for M is given by x of z equal to the real part of the integral, the first component, the 1/2 of the 1 over g minus g, times the dh, second component, the I over 2 times the 1 over g plus g times dh, and then the height, the third component, dh. Note that if the domain sigma isn't simply connected, then the integral may depend on the path of integration. This is called the period problem. The Weierstrass representation is represented by the triple, the domain sigma, together with the Gauss map G and the height differential dH. So some examples of some surfaces and their Weierstrass representation. Enneper surface, discovered by Enneper in 1864, has genus 0, 1 end, is not embedded. Weierstrass representation is g of z equal to z and dh equal to z dz with the corresponding parameterization. Catenoid, Weierstrass representation is g of z equal to z and dh equal to 1 over z dz. Helicoid has Weierstrass representation g of z equal to z, same as the catenoid, and dh equal to the I over z dz, versus the catenoid was the 1 over z dz. So the helicoid and catenoid are referred to as conjugate surfaces of each other. One thing to note is that building blocks of minimal surfaces typically are given by the catenoids, helicoids, and planes. So here's this k-noid, a 5-noid, where I'm taking this surface and combining it 5 different catenoid ends together in a surface. So the location of the different pieces, in this case the 5 catenoid ends, isn't rounded. They need to be balanced in an appropriate manner. So in this case, the catenoid ends of the k-noid are located at the kth roots of unity. Most known examples of minimal surfaces have non-trivial reflectional and/or rotational symmetries, simply because they're easier to construct and easier to then solve the period problem. So this 5-noid has some reflectional symmetries and obviously rotational symmetry as well. With Weierstrass representation, the g of z equal to the z to the k minus 1 power dh z to the k minus 1 divided by the z to the k minus 1 squared dz. Variation on the k-noid, this vase of catenoids. So here we have one downward catenoid end with vertical normal, one planar end with vertical normal, and then k catenoid ends pointing up with non-vertical normals located at the kth roots of unity as well. Weierstrass representation here is given by the g of z equal to rho times z to the k minus a to the k, and dh, a to the k minus z to the k divided by z times z to the k minus 1 quantity squared, dz. Shirk's surface, W product surface, the Weierstrass representation is g of z equal to z, dh equal to z divided by z to the 4th minus 1, dz. Conjugate surface to Shirk's doubly periodic surface is Shirk's singly periodic surface. Weierstrass representation, the g of z equal to z, and the dh, the iz, divided by the z to the 4th minus 1 dz. A minimal surface is called doubly periodic if it is invariant under two linearly independent translations in Euclidean space. So here's a building block of Shirk's doubly periodic surface. So we can see the two period vectors here in the two horizontal directions. And then showing more of the surface, we can see that period vector then repeated as we go along in that direction further, and this period vector repeating the surface again in that direction. And of course, we're just repeating forever in all the directions. And these pieces going up here, they don't stop as well. They're asymptotic to half planes, so they just keep extending up forever on each of them. Some properties of doubly periodic minimal surfaces due to the work by Meeks and Rosenberg. If we assume M tilde is a properly embedded doubly periodic surface such that the quotient has finite topology, we'll let lambda be the group generated by the two translation vectors. The quotient M equal to the M tilde mod lambda is a properly embedded minimal surface in the R3 mod lambda or T cross R. M will be diffeomorphic to a compact Riemann surface with a finite number of punctures. And the punctures correspond to those annular ends asymptotic to half planes of the quotient surface, which are, as I said, are asymptotic to half planes in the M tilde. Assume the period vectors are horizontal. By the half-space theorem, M has ends extending above and below any horizontal plane. So these are usually referred to as the top and bottom ends. M has finite total curvature, C of M equal to 2 pi times the Euler characteristic of M. M separates T cross R, and the number of top ends of M as well as the number of bottom ends of M is even. And M has at least 4 ends. If the ends of M are parallel, then the number of top ends equals the number of bottom ends, and the number of ends will be a multiple of 4 in that case. If the ends of M are not parallel, then they are vertical and T cross R has a commensurable lattice. The theory of doubly periodic surfaces splits into two cases depending on whether the top ends are parallel to the bottom ends. We refer to the two cases as the parallel case and the non-parallel case respectively. Due to some work by Hauswirth and Trizet, if M has parallel ends, then it's a smooth point of a three-dimensional moduli space. If we fix the direction and length of one of the horizontal period vectors, in the parallel case, the parameters of the moduli space are given by the length of the other period vector, the angle between the period vectors, and the angle between the vertical axis and the flux vectors at the ends. Also due to Hauswirth and Trizet, if M has non-parallel ends, then it is a smooth point of a one-dimensional moduli space. In the non-parallel case, the parameter is given by the angle between the period vectors. Meeks and Rosenberg proved the period vectors must have the same length if the number of top and bottom ends are the same. And it's easy to show that the flux vectors must be vertical. So the doubly periodic Shirk surface has genus 0 and 4 ends. Its quotient surface is diffeomorphic to a 4-punctured sphere. So again, each of these 4 punctures here on the sphere, they correspond to each of these annular ends in the quotient, or the half planes if we're viewing the surface in R3. Some known examples of doubly periodic surfaces. So as this genus 0 non-parallel ends, the doubly periodic Shirk surface, again discovered in 1835. And note the angle between the ends, between the top and bottom ends, varies between the 0 and 2 pi, but never equals 0. As the angle goes to 0, the surface converges to a helicoid, if scaled appropriately. Lazard, Hawley, and Meeks in 2001 proved that these are the only genus 0 doubly periodic minimal surfaces. Some known related examples, some higher genus examples with non-parallel ends. There's one known example for each genus G greater than or equal to 1, with the handles added between every other pair of ends. So Karcher in 1993, he constructed a genus 1 example with orthogonal ends. Douglas in 2008 proved the existence of the sheared genus 1 examples in which the angle can be varied between the 0 and 2 pi. The surfaces limit as a singly periodic genus 1 helicoid as the angle goes to 0. Weber and Wolf in 2012 used Handel addition to prove the existence of the higher genus examples in the orthogonal case. So those higher genus examples, they should also, as the angle varies between the 0 and 2 pi and goes to 0, they should ideally, we conjecture that they'll converge to the genus G example would then converge to a genus G helicoid. Some known examples with parallel ends. So with genus 1, the three-dimensional family of genus 1 surfaces with parallel ends was constructed by Karcher in 1988 and separately by Meeks and Rosenberg in 1989. And Perez, Rodriguez, and Trezay proved that every genus 1 doubly periodic minimal surface with parallel ends lies in this connected family. So here's one example. We can also shift the top ends while keeping the location of the bottom ends constant, and shift the top ends over, just giving some of the sense of this three-dimensional family of the genus 1 doubly periodic surfaces with parallel ends. Wei in 1992 found a one-parameter family of genus 2 surfaces. He took the KMR surface and then he added these handles between every other pair of ends. Rossmann, Thayer, and Wolgemuth found a different one-parameter family of genus 2 surfaces by adding handles to the other alternating pair of ends of the same KMR surface. And then Rossmann, Thayer, and Wolgemuth, they also constructed a genus 3 example with handles between every pair of ends of that same KMR surface. And then myself and Weber in 2002, we proved this theorem, that for any genus G greater than or equal to 1 and any even number, capital N, greater than or equal to 2, there are three-dimensional families of complete embedded doubly periodic minimal surfaces in Euclidean space of genus G with n top and n bottom ends in the quotient. So here's two views of a genus 7 doubly periodic minimal surface with parallel ends. And then here's another, a genus 4 surface.